Go for him.
I just put up 2.
In the morning.
Where were you freezing your tail off?
Yeah.
Just at the field site.
Oh,
Morning.
Morning. Oh, shoot, this is.
hey Jason.
So, you good, Ariane?
Okay.
Good.
I even brought my insulated.
Are you?
You hear me?
Yeah, I can hear you.
Yeah, great. We tried at the same time.
Yeah. So I was trying to call Ramesh as well and do 2 at once on here, which works as long as he picks up. And he hasn't picked up. So I might hang up with you and then try that again.
All right.
If not, we might have to get another computer going.
Okay.
So.
Hello, Ron.
Good morning, how are you?
Good morning. How are you doing?
Good.
Good.
Do you want me to go get this on the computer?
Sure, that would be great.
I'll be right back.
Thanks, Amy. What time is it there? You're about 4:57?
Oh, no, it's 3.
3:57. Okay, 3 p.m.
Not too bad.
All right.
Bye.
So are you in Wuppertal? Eric, are you in Wuppertal?
Yes, I'm in Wuppertal in my office.
Yeah.
It's 3 p.m., so it's not so bad.
Okay.
Okay, I'm gonna hang up and then try to call you back.
Okay.
Call you and Ramesh at the same time and see how that goes. Whoa, that worked.
Seems to work, yeah?
Okay, yeah, so now we're just waiting for Dr. Reddy to join. So you have a good signal, Jörg?
Yes.
Okay, good. Yeah.
No.
Yeah, how you doing? No, you didn't. I haven't started yet.
I'm sorry.
Yeah, he should be on here. It's just. Yeah, there's your.
Hello, good morning.
I think it sounds like he just came on. Or he just went up.
So.
Try calling Dr. Ray again. Yeah. And we're broadcasting live on YouTube. Yeah. So my mom. Yeah. Yeah. So keep it tame.
I'm not trying to hide. You might have to see me.
Still not on.
Yeah. Yeah.
You want to stay. I'll see if I can bring them up and then you can at least use this computer.
I need to stand here for you to see it. You don't need to see me. Yeah. You have the slides right here.
I have this one.
Can you call something?
Yeah.
Yeah, I can. Just use the phone here.
Ramesh, this is on. Fine, we're trying to get people linked up. To the Skype.
What's his contact up?
Conda ready?
So you log in.
Is it the same?
Yeah.
KONDA. RUBBY.
Yeah.
Okay. So this is your name and his name.
Yeah.
So, I love him. So we can talk to you a second. Yeah, just a second. I got the name.
So do you see an incoming call from me right now?
All the time, actually. It's 4 minutes, it's an incoming call from.
Yeah, I can do that. So what, okay, what is that, KRR? See there. It says that I tried to make a call, but that's the same.
I can probably get it. Hold on a second. There he is. I got him.
Okay.
Tell him I'm calling him.
Yeah, did you see the call coming in from Amy? Yeah, that seems to not be working.
What's the other one? It shows it as 10, but it's not.
Yeah, you could, if you'd like, you could call me. Okay. Yeah, it's the name is J.S. LeMonte. I'm trying to call you right now. Do you see that? Okay. Yeah, I'm not sure.
It's ringing for me. It's ringing for me.
Okay. I mean, it says that it's ringing for you.
Yeah. Is he a call from me?
Do you see a call coming in from Amy? Yeah, I've got I can send you a link to where it is. It's streaming online on YouTube as well.
Well, oh, yeah.
I'm going to send it from my wife's email.
Okay, so you're just going to do that later? Okay. Yeah. Well,
And I just sent it so you'll follow that link. Okay. You good?
all right. We'll put this over there.
All right. Great. Thanks. Then I won't be able to hear you, but we'll get you on the phone when the presentation's done. Is that okay? All right. Thanks.
Okay, good morning, everyone. I think we're ready to start. So I'd like to welcome all of you here to hear Josh LeMonte's exit seminar, part of his PhD program dissertation course. We have a couple of committee members on Skype and offline. We have Jörg Klebe, who's at the University of Wuppertal in Germany, and Professor Ramesh Reddy, who is at the University of Florida, but he's in Washington, D.C. So I'm going to turn it over to Josh and, of course, Ryan Patero from Brookhaven National Lab and Shover from the Department of Plant Science, for science of our committee members. So Josh will give an overview of his research, and then we'll open it up for you as the general audience members to ask questions, and then I'd ask you to leave, and then the committee will Josh, turn it over to you.
Right. Thank you, Dr. Sparks, and I'm excited to be here and to be doing this. It's been a long time coming, it feels like, but at the same time, it also feels like not too long ago, Sarah and I showed up here in Delaware. So it's a bittersweet day. So my research has focused on the potential impacts of sea level rise on arsenic mobility and cycling in contaminated coastal soils. And I wanted to start today by acknowledging my funding sources, because really without them, happen. So my fellowship through the Department of Defense, the SMART Fellowship, as well as the EPSCOR NSF grant, I'm grateful for the funding that's come through that. Now, sea level rise is happening, and it's really climate change induced. And it's happening at a faster rate than it ever has. In fact, if we were to go to the beach, like we were at Dr. Sparks' beach house this morning instead of here in the conference room, which maybe some of us are wishing we were. Yeah, all right. Yeah, that's whoever's next. Having to talk about beach. But if you went down there and you put your feet in the sand, today the water would lap up onto your feet. But if you stayed there for 100 years, to the year 2100-ish, then the seawater would be up to your waist. And that's about the rate of sea level rise that we're seeing. It's about 1 meter of sea level rise is expected over the course of the next century. Now that stands to impact some obvious things, right? That stands to impact infrastructure, like Dr. Sparks' beach house might be beachfront in the 100 years. But it also stands to impact more unseen things. And that's really what my research talks about is those hidden dangers that are lurking due to this sea level rise, looking at how the chemical changes will occur as the sea levels rise. And Delaware is an ideal place to look at that because of its long history of industrial activity and legacy contamination. And so what I'm going to try to do today, and I've tried to do over the last 5 years or so, is bring these things together, right? So look at sea level rise, the history of contamination here in Delaware, and arsenic, and how those things are all interacting, and really try to meet there at the nexus, so where they all come together. Now, to get started, I want to give a little bit of background on arsenic itself. Arsenic is infamous, you might say, for what's been deemed the largest mass poisoning in the history of the world through the contamination of drinking groundwater wells in South and Southeast Asia. And the arsenic that occurs there that is impacting human health through causing increased cancer rates, as well as arsenicosis, like you can see here in these hands and feet, those lesions that show up. The arsenic that's showing up in this region is geogenic, or it's naturally occurring. However, closer to home, the arsenic is occurring and it's not natural, but it's industry anthropogenically input rather than geogenically. And it's been put there through a history of industrial activities such as tannery, so tanning leather. Wilmington, Delaware was the largest tanning. It was the tanning hub of the United States around the turn of the 20th century. Additionally, chemical production, ore processing, all of these things have led to increased arsenic levels. And lots of times when these industries use arsenic, the arsenic 3 or the more chemically active form is used. But that chemically active form is also the more toxic form, the more mobile form, and it's typically thought to be the most dangerous form. But lucky for us, soil is a pretty cool thing, and as it goes through these natural processes, it can be oxidized or changed from that arsenic 3 to arsenic 5, and that arsenic 5 is less mobile. It's still toxic. You still don't want to be playing in some arsenic 5 soil too much, but it's more stable. It's less likely to move. And that change from arsenic 3 to arsenic 5 occurs by some abiotic processes as well as some biotic processes. Now that arsenic that's in the soil, it can also change again through either direct reduction processes or the reductive dissolution of the soil particle, the soil iron that's holding onto it. So if the iron is dissolved, then it can then lead to the arsenic being released, and again becoming more mobile. Now all of that is what's currently happening. Now, what I want to talk about is how sea level rise could be impacting that. Now, sea level rise is occurring as a combination of things. So this is a video that's going to show you one of the ways that arsenic is, or that sea level rise is occurring, and that is the melting of land ice. This is the Mendenhall Glacier in Alaska. So the melting of land ice in combination with thermal expansion of oceans. So that red indicates 3 years previous, and it's showing you over the course of a 3-year period how the melting of the land ice at that glacier is proceeding. And this is a widespread global phenomenon. So the combination of this, thermal expansion of the oceans, and then also subduction of coastal zones is leading to the rise in seas. And that stands to impact millions upon millions of people. Around half of the world's population lives in coastal zones. 44% to be exact, the United States 53%, and in some nations such as China and Brazil, you see even larger percentages of the population. So how will sea level rise impact what we just talked about, how arsenic is behaving in the environment? And the question really is, will there be newly formed flooding zones? How will this saltwater inundation affect it? How will these waters with increased ionic strength impact it? Will the arsenic be mobilized? Will it be immobilized? Will it precipitate out with like sulfides and even under reducing conditions not pose as much of a threat? And the objective of my research is to determine how these changes will impact how arsenic moves and how in these historically contaminated soils and how it will move. And Delaware is an ideal spot to study it, like I said. So it's, and you guys here know a lot about Delaware, everyone who's here, but you know, my mom who's watching is not so familiar. So I'll go into a little more details about that. And I want to talk about the past. So I've done that a little bit, but what's led to the arsenic being here, talk about the present, what's happening currently with this coastal arsenic, and then go in and talk about the future or what will happen as the sea levels rise. So that's kind of the path that we'll take. So like I said, Delaware is an ideal spot. It's here in the Mid-Atlantic region. It's the lowest lying state in the country with an average elevation of 60 feet. And not only that, but it's also has its fair share of contamination. If you look at this map, each one of these black dots is a contaminated site. Each one of those purple circles is a Superfund site. So there's no shortage, right? But if you want to identify research sites that are contaminated, if anybody has done that, you know that it's not so easy to get access to those sites. And really that was, you know, as I was going through my PhD, it took a long time to find a site that we could use. But luckily the folks at DENREC and some environmental consulting agencies around worked with us and were able to get us there. So we were able to locate some research sites in Wilmington, which has more than its fair share of contaminated sites. And I want to mention here too that this isn't just an environmental issue, but these red areas indicate where more than 10% of the families are below the poverty line. And a lot of times where this contamination and sea level rise are coming together are also areas where people don't have the resources to move. So this is a social issue as well as an environmental one. And we've been able to collaborate with some sociologists and economists to try to understand people's perception of risk and how it's really going to affect them, how they see it. But for now, we were able to identify these sites, and this is the site that I'm going to talk about today. And this is a ditch site. We worked with DENREC. They were able to help us get access to this site because they saw that this ditch that they built 20 or so years ago as part of some remediation efforts for some adjacent contaminated sites. When they built it, it had some high arsenic levels, like around 100, 200 parts per million, which is about 10 times the state of Delaware's background level, which is 11 parts per million. But over the course of the next 20 years, it accumulated at a really impressive rate, and to the point now where there are levels in excess of 13,000 parts per million. We're talking percent levels of arsenic in these soils, which is scary and really high, and they didn't know what was going on. And so they knew that we were looking for a site, and they came to us and said, hey, if you help us try to figure out what's going on here, we can give you access to the site. We said, great, sounds like a good idea. So we went out with two objectives. One is to understand how the arsenic is dynamically moving right now at this site, and then also to look at where that arsenic is coming from in the ditch. How is it getting there? And the folks at DENREC, they went out and did some thermal imaging in the ditch, and they went out on a cool morning and looked, and with this infrared technology, they were able to identify a hydrologic seep. So a spot where the groundwater was entering the ditch. And that seep was the same spot where they found the highest levels of arsenic. And so that gave the clue that, all right, this arsenic is coming, it's moving laterally through hydrologic flow. And so maybe it's coming from one of those adjacent contaminated sites. So we went out and monitored the arsenic dynamics in the field at this ditch. We used some existing wells that were installed thanks to folks giving us access like Clay here. And we started in the fall of 2014. And we went out and we didn't just use their wells, but we also installed our own instrumentation. We installed EH sensors every 15 centimeters from the surface down to about 3.5 meters, as well as pore water samplers at 3 distinct depths. And that led us, or with the hope that it would give us insight as to what's happening with the arsenic. How is it moving? How is it changing over time? And so this is the kind of data that we got, and this is looking at the EH across depth and across time. So this here is the surface, and we're moving down in the soil profile, and this is over about a 3-month period. Now we have this kind of data for the last 20 months, but the screen won't fit that much data, so this is a representation that is just to show you that there's a big range of redox condition there that's present in that soil profile. So moving from very reducing, we have what looks like a perched water table at one point, and then even to very oxidizing condition. So there's a wide range, and arsenic is directly affected by EH. So that gave us a clue that the arsenic was going to be an interesting thing to look at here. And it let us look at the capillary fringe. So below this, about 2 meters, 1.5 meters, is where the water table typically sits, according to the wells that we monitored. And you can see there that you see that in the EH. So looking at what we found there, looking at the chemical dynamics of the pore water samplers that we, this is just the range that we saw over the course of time from the samples. And we went out and we sampled every month. Sometimes we did some more intensive sampling, and this is a combination of all of that, just looking at the chemical dynamics in this pore water. And so we've got arsenic, iron, EH, pH, DOC, things that typically impact how the arsenic moves. And what I want to focus on here is just looking at these levels. So this is in 10,000s of ppb, right? So the drinking water standard, as established by the US EPA, is 10 ppb, and we're talking about 1,000 times that in this groundwater. So we're seeing high levels of arsenic in the groundwater. And it's closely or well correlated with the iron concentrations and iron 2 concentrations that we see in that same pore water, which gives us a clue that it's going to be closely tied with or related to the reductive dissolution of those arsenic-bearing iron oxides. Now, so that's kind of the first objective. We saw that it moves, and Schwann has done some more work looking at the dynamics, how it changes over time, seasonally, and shorter than that, and longer than that. But the second objective was trying to understand whose arsenic it was. And John Cargill from DENREC, when he approached us about this, he said, I don't expect you to be able to find anything, like to figure out anything. But if you can say, like, you don't know whose arsenic it is, then that's good for us. But we said, well, we'll try anything, right? So we used some bulk characterization techniques as well as some more cutting-edge synchrotron-based techniques to understand whose arsenic is coming to the ditch. And the Superfund site had higher arsenic than the Hazardous Substance Control Act site. And looking at the flow, the hydrologic flow, it makes sense that both of them are flowing towards the ditch, so it's plausible that either or could be contributing to, or both. And so looking at some of the characterization that we did, we went out, we took soil cores, and there's quite a bit of heterogeneity as you move down the soil profile. If you look at some of these pictures here, you can see in this 1.5 meter core, it might be hard to see for some of you, but it goes from a bright orange to purple to a dark brown. And just looking at the colors there, it indicates that there's some serious changes happening in the short amount of time. Or this section here that was like in a 5 centimeter section, and it goes from orange to green to orange to purple to black. This isn't your typical soil, right? This isn't your typical AOMC soil profile, right? But looking at the cross depth, this 0 to 1.2 or above the water table, the 1.2 to 2.4 are at the capillary fringe, and then it's below the water table, below 2.4 meters. We're looking at arsenic, iron, sulfur, and pH. Again, important players in this story. But what I really want to focus on is the blue and the green bars, because those are indicative of the hazardous substance site and the Superfund site, and that middle zone, because at the capillary fringe is where you're seeing the most dynamic changes, and also because we were able to get sample from all the sites at that depth. Some of the sites, because it was so saturated, it was hard to retrieve the sample. But if you look here at the arsenic, there's more arsenic at the Superfund site than the hazardous substance site. That's what I said. But if you look at the iron in the soil, there's significantly more iron at the hazardous substance site than the Superfund site, which could lead to, that's more sorption sites for the arsenic. Arsenic can be held more strongly in that area, potentially because of that. And then skip to sulfur and look at the pH. Normal soil pH is like 6 to 7, like it's normally circumneutral. But this pH, we found pH levels in excess of 9 in this area, which is crazy high. And if you think about arsenic sorption, it kind of follows an envelope, meaning that across pH, that at low pH, you see less arsenic sorption, and at high pH, you see less arsenic sorption. So these really high pH levels are in that zone where you start to see less arsenic being held onto by the soil, because you're reaching a point where you're in excess of the point of zero charge of those particles that are holding onto the soil. So that's a clue that perhaps because of this high pH, and the higher arsenic, that maybe the Superfund site is more susceptible to release of the arsenic than the hazardous substance site. But there's some more that we can do, right? So we use a more cutting edge technique looking at synchrotron-based X-ray absorption, near-edge structure spectroscopy, or ZANES, as a fingerprinting technique. So just like each one of us has unique fingerprints, you know, that's how you unlock your iPhone, chemicals also have unique fingerprints. So oxidation states of arsenic, for instance, have a unique spectra, which are shown here. And so going to the national lab, here's a shout out to X27, which is long gone in the fire, but we're excited for the new beamline. So what you can look here is looking at the standards, so the known spectra compared to the unknowns. And for the most part, if you look, this is arsenic 5, or that less mobile form of arsenic. And most of them line up pretty well with that, just looking at it. But you can also see that there's this little bit of a shoulder that forms for some of them. And so looking at it can only get you so far, right? And that's why these gray dots indicate fits, and using linear combination fitting, we're able to look at the percentages that can be attributed to the contribution of arsenic 3 or arsenic 5 or an arsenic sulfide in that sample. And so again, these are highlighting the that more interesting area, the 1.2 to 2.4 meters. And this here is the ditch sediment. So in the ditch sediment, it's very reducing, lots of arsenic 3, which means that the arsenic that's there is pretty mobile, which, if you remember, it's in like 13,000 parts per million. So 13,000 parts per million of 90% arsenic-free arsenic is not something to bat an eye about. It's something that should be taken care of, and hopefully we can help determine whose this is. And really, that same site where there was higher arsenic, there's a high pH, there's also the highest percentage of arsenic-free. So the Superfund site from 1.2 to 2.4 meters, you see 40% attributed to arsenic-free, which is basically saying that looking at the Superfund site, it's more likely that the arsenic could be flowing from that than from the hazardous substance. So that's kind of the take-home message from that, is we were able to, not definitively, but using some clues, figure out whose arsenic potentially could be entering that ditch. And so the conclusions really are that the arsenic is dynamic in the pore water, and they're strongly correlated to the iron, which means that reduction of solution can be driving the release, and that the Superfund site could possibly be more susceptible to releasing the arsenic to the down gradient bit. So, just to review, so we talked about the past, we talked about how the arsenic got into the soil, we talked about the present, the dynamics, and how it's moving. Next, we want to talk about the future and how sea level rise will impact that arsenic that exists there. So how we did that was through some lab experiments where we were able to use some biogeochemical microcosms to simulate flooding with river and seawater. And we did that with natural waters, both river water collected from a tidal river here in Wilmington, and then seawater that we collected down in Cape Henlopen. And I want to point this out for a second. This is one of the Denon scholars, Priyan Esquivel, who helped with some of the research one summer, and he was brave enough to go for a dip and get the ocean water that we use. And I'm a little sad that he's not here to see this. I showed him this picture, and he was like, "Yeah, those shorts are too short." But I really appreciated his help as well as everyone else who helped in this. This is all of this stuff that I'm showing you is not just me, but I've been lucky to work with a lot of people to collaborate to help get it to where it is today. And so using these microcosms in the same soil that we collected in the ditch, we wanted to use them at field relevant levels. So I guess my son is tired of the presentation. And that's really, by deploying the instruments in the field, we were able to see the conditions that are existing there. So bringing it into the lab, we could mimic similar conditions. And so that's what we tried to do. We closely were able to control the pH in about 40 millivolt increments. And we took it to more reducing levels and didn't get it quite as oxidizing, but it's similar levels as well as for the pH. So they're realistic. And just to give you a little bit of detail, the river water, its pH was 7.2. The ocean water was a little higher at 7.8. And these are pretty big vessels. I actually did this in 4-liter vessels. And we were able to go in, stir it around, pull out a sample, separate the solid from the solution, and then analyze both. And this is the kind of data that we got. And this is showing the reductive potential of the EH and the pH throughout the duration of these microcosm experiments. The river water is on the top in the orange, and seawater is on the bottom there in the purplish colors. And that's going to, those color coordinations are going to follow suit as you go through the rest of the topic. So just remember, river is orange, sea is purple. You can see that. I'd be impressed. I'll try to remind you. And what this is showing is just that how we did it. We drove down the EH by adding some carbon, and then we were able to equilibrate them at targeted EH zones for 72 hours, and then pull a sample, then move to the next zone, equilibrate it there, pull a sample, and so on and so forth. And so we drove the EH down in those solid lines, and then the pH followed what is a pretty typical pattern that as you drive pH down, pH increases. So typically inverse. And what we found when we pulled those samples is that there was more arsenic released from the river water than the seawater, which was a little surprising, but I don't really know why. But we did analyze some other factors that gave us some clues, and I'm going to get into that. But I have two hypotheses as to why or how this difference is occurring. The first of which is that there could be preferential sulfate reduction. Right? So normally, this represents a sulfate molecule being reduced to an H2S molecule, and typically, if you look at a redox ladder or the energetically favorable pattern, microbes will use in dissimilatory processes. They'll utilize iron oxides before they utilize sulfur compounds as their terminal electron receptor, but not always. So typically, it's iron is easier for them to use than sulfur, but sometimes, depending on the iron form, it could be easier for them to utilize the sulfur. So there's still some work that needs to be done to really understand if that's what's happening or not. The other one is that the increase in salts, the high salts, could just be messing with the microbial community, inhibiting the microbial action. I mean, it's just like if we were to drink salt water for a day, our activity level would be inhibited, right? So microbes are little creatures. I could see how that could be affecting them too. But that's another thing that in the future we need to look at. But what we did look at are some factors that are related to arsenic release. And I looked at some sulfides, so testing that first hypothesis. And unfortunately, our detection limits weren't that low. They were around 1 part per million of like reliable detection limit, and most to all of what we measured was below that. And that's really because sulfide isn't very stable in solution. It quickly transfers to something more oxidized. But because there's no significance here between sulfur in solution and arsenic, that kind of, or sulfide in solution and arsenic, that kind of says, well, maybe that first hypothesis of sulfate reduction, that might not be it. But then looking at these others, alkalinity, DOC, these are both indicators of microbial activity. And both of them are well correlated, significantly correlated to arsenic in solution for both seawater and river water, which is a hint that it could be microbially mediated. We know that the reductive dissolution of iron oxides that leads to the arsenic release is a microbially mediated process. And so this is no surprise, but it gives reason to look into that second hypothesis of how these higher salts are impacting the arsenic release, the microbial condition. So, but just like in the field where we could do some stuff with the solution, but only get so far, and then you need to go to some more advanced techniques, we did the same thing here where we looked at arsenic, zanes, across all of these EH zones where we pulled a sample. So again, what we did was we went from reducing to oxidizing and pulled a sample. And if you look at these spectra or these, fingerprints, you can see if you pay close attention that there is a trend. So looking at the river water, as you go from these darker spectra and move up into the lighter spectra, you see this shoulder here growing and growing and growing. So that's indicating that we're seeing arsenic shift from predominantly arsenic 3 or the more reduced form to more contribution from arsenic 5. And a similar thing you see in seawater where there's more and more influence from that higher energy fingerprint. But again, looking at it only gets you so far. So this figure here is showing the linear combination fitting, which are those dotted lines next to the spectra. And what I want to focus on first, that I think is really the story here, is the triangles or the arsenic 5. So if you look at the arsenic 5 and you compare them at the most reducing conditions, so the lowest pH values, there's a lot more arsenic 5 in the seawater than the river water. And then when it becomes more oxidizing, then they get closer together. But this big difference is showing something that is similar to what we saw in solution. Right, so when the arsenic is released, we see more arsenic in solution, arsenic 3 in solution, and here when we see more arsenic 5 on the surface, that's corroborating that. It's saying that the arsenic is more stable under those reducing conditions. And so as you move from reducing low oxygen levels to higher oxygen levels, you see arsenic 5 increase, and you see an inverse relationship with these squares or the arsenic 3, that as you go from reducing to oxidizing, you see the arsenic 3 contribution decrease. And in the river water, we saw more arsenic 3 in solution. So, or arsenic 3 on the surface.
What is what it started as? What was the soil before you put it in the water? Was it all arsenic 3 or arsenic 5?
No, it was mostly arsenic 5. So the soil so it was the ditch soil, and the ditch soil in its natural state, so if we go out and sample it, preserve it, take it to the synchrotron and look at its speciation, it's mostly arsenic 3. But we didn't take that's, wet, preserved sample and put it into the microprocessor. We dry the soil, we homogenize the soil, we put it through a 2 millimeter sieve, and then we put it in. So we gave it time to go ahead and go through that oxidation process and shift. I mean, you could see it. It went from a gray soil to an orange soil through the process of drying.
You think it all starts with 5 when it goes into the
I
reactor?
think it's predominantly 5, yeah. And then to look even in more detail, we did some micro zanes, or so these are micro focus techniques and X-ray fluorescence, just to corroborate what we saw with the bulk thing. So those spectra that I just showed you were the average over the whole soil. It's a larger area that the beam is hitting and the signal you're receiving. This is more focused. This is more like you're looking at single particles rather than an average. And there's a lot of information here too. These are the X-ray fluorescence maps showing the elemental distribution. And from these maps, we were able to identify hotspots where there's high arsenic and then analyze these. Each one of the maps, we identified 10 of them and then looked at distinct phases, and so, or signatures, and at the designated pH, whether it's really oxidizing or reducing, and we saw the same thing. I mean, it's, I think for the sake of time, I'll say that. So what we saw is that there was never anything in these microzanes that we didn't see in the bulk zanes. And we also looked at sulfur zanes, so not only arsenic, but also the sulfur, to see if that can give us a clue if there is that preferential sulfate reduction. And if you look at this second peak in this spectra, that indicates the more oxidized sulfate species. And if there was a big difference in how they were behaving, it would give a good clue that perhaps, yeah, in the seawater, we're seeing preferential sulfate reduction, which would preserve the arsenic on the iron oxide. But again, this is the seawater in the purple, the river water in the orange, and if you just look at the amplitude of the spectra, you can see that it gets dampened as you go from oxygenated to the lower oxygen system, the lower EH. For both the river water and the seawater, which means that we're seeing the same thing in both of them, which again might say that first hypothesis that I have needs some work. But the experimental conclusions, what we found here is that arsenic is released as EH is decreased. So when there's flooding conditions, arsenic will be released in high concentrations, most notably below 0 millivolts. And we saw it higher in the river water than the seawater, and we saw more arsenic-3 on the soil surface in the river water than the seawater, which makes sense when we talk about more river water releasing arsenic-3. So what that means for a sea level rise is that climate change-induced changes, flooding, will lead to arsenic being released. And how exactly it changes it really depends on the water, for instance. So we saw there's a big difference between the seawater and the river water. And this data shows that maybe seawater will lead to less arsenic release than river water. But I also did a similar study with same parameters, different soil that I collected like 3 miles from that, and it showed the opposite. So it showed that we saw more release with seawater than river water. So seawater is blue and river water is orange. So these soils are very different. And so what I really want to do by showing this to you is show you that we can't just take a wide swath and say that this is how it happens. But really, we need to do more research. We need to understand how different soils are going to react to this. So to summarize, arsenic has been deposited in the past for industrial activity, and some of it has been naturally attenuated. That naturally attenuated soil stands to be changed and mobilized. And presently, we see that the arsenic is still dynamic, it's still moving, but sea level rise stands to make those changes even larger. Areas where there's arsenic in the soil currently could see that arsenic release migrate to the groundwater, migrate upwards, get in and pose a greater threat than it currently does. And so, as an outlook, as far as where I see this research going, I think that one thing that we should do is try to determine the mechanisms here, right? One step is looking further into that microbially mediated process theory, looking into like how the seawater inundation is impacting those soil microbes. And then also looking at the mechanisms is looking more into the influence of sulfur on arsenic mobility and cycling in these sea level rise scenarios. And then also, I think that we could do some work to enhance the fundamental understanding, and that's just looking at model systems. So looking at how arsenic could sorb onto model soil constituents, iron oxide, manganese oxide, clays, and just see how it will sorb onto these particles across well-defined pH zones. And then enhance the scope. It's maybe bring in more soils. You know, like I said before, sea level rise is a global issue. Contamination along these coasts is a global issue. And so if we could get our hands on some of the soils from around the world and then replicate this, it would really help us understand what, you know, if there are any trends that we're seeing across the globe. So with that, I want to say thank you again to my funding sources, to DENREC for all of their help, for the national labs and them giving us time at the beam lines, and my advisor, Dr. Sparks, the doctoral committee, Dr. Reddy, Dr. Schober, Dr. Pero, Dr. Vitleva, and I've got a long list here. I'm going to read them all. There's Jerry and Jason and Schwan and Polly and Dalton and Caroline and John and Marion and Frieden and Miles and Ben and Jamie and Mark and Jen and Brandon and Kathy, Beth and Amy and Jeanette, my parents, my wife's parents, the rest of our family and friends, and of course our research group. I tried to put all of the, or most of the group photos that we've taken since I've been here. It was fun to go back and look at all of us change. I won't say for the better of words. And of course, last but not least, my beautiful wife, Sarah. I think if it weren't for her, I don't know if I would have finished this thing, but I think she encouraged me to keep going enough times that it would. I'm happy for her. So I'm grateful for her for that. So with that,
Okay, any questions from the audience?
okay.
So, your second hypothesis is that the soil water will affect the microbial activity. So I would say the microbial activities we're talking about is first arsenic reduction and iron reduction, and also the sulfur reduction, like that, right? So if you were talking about that, you should be able to see the iron too, a difference between the the two treatments, and also the arsenic speciation will be different if you were to see what are the real treatment.
Yeah.
If you have any comments with it?
Yeah, and that's a good point. And I think that that's part of the reason why that pointed me towards that sulfate reduction. hypothesis a little bit. Well, I don't know. The iron 2 in solution was practically the same for both of them. Wait, no, that's fine. So the iron 2 was decreased in solution for the seawater as compared to the river water, and the arsenic in solution was less with the seawater for the river water. And so because there was less iron in solution, there was less arsenic in solution, that made me think that the reductive dissolution of iron oxides was being hindered. Right? And so that made me think, well, maybe that's why, maybe they're using something other than iron oxides, like sulfur. But yeah, I think that you're right. Those are good indicators, and that's really why we measured what we did. Right? That's why I tried to get a glimpse at sulfur, iron 2. We measured all of those, and I think there's still nothing to it. But you're right. Looking at this, the speciation was really hard because of the high salt. There's too much interference on the ICP to get the reliable results. So those are really good points.
I'm sorry if I missed it, but was the river water native to the sample soil sample location?
Yeah, it's straight out of the Christina. Not that.
This is just a curiosity kind of thing, and kind of company name. But what kind of industry on this?
There was a chemical production facility on the Superfund site, and there was an ore processing facility on the hazardous site. Yeah, but I can't tell you. You can ask Clay later and see if he'll tell you.
So was the chemical plant doing arsenic trioxide?
Yeah, so they used arsenic trioxide.
And then the ore was a pyrite ore, an arsenic pyrite ore?
The question.
I think yours has a question.
Could you hold yours till we get ready for it?
I'll repeat them.
Other questions?
From my uneducated perspective, why is it that the arsenic levels in the ditch are higher than from either the Superfund site or the hazardous substances site? And then you said that they built that ditch about 20 or 30 years ago as a remediation effort. And it seems like that would be counterintuitive because it looks like it's connecting the arsenic to our water in the river.
Yeah.
Flushing it out. That's their remediation.
Yeah. Dilution's the solution to pollution, Rich. No, thanks. Yeah, so the question was, why is there more arsenic in the ditch than at either of the source sites? And then why did they build the ditch in the first place? It's funny that you asked that, Rich, because Sarah and I were talking about that yesterday when I went through this with her. She's like, why did they build that in the first place? My understanding is that it would help direct surface flow. I don't know, Clay, do you have?
It was there already.
Okay.
So it was a roadway drainage ditch. It was remediated and reconstructed as part of it.
Okay, so they put like some riprap in and they put some stone in.
Right. And like a geotextile. Right. But there were already pipes under the roads. And, they, rather than, and this was before my time, rather than extending those pipes all the way out to the river, they ended in the filled up.
You expect with a ditch in an area where you haven't had that.
If you get this great tea bag.
Yeah.
And what's interesting is, as Josh said, they're much higher than they were before.
Yes.
The ditch was already there.
So that gets.
So that's an interesting question. Maybe that's a follow-up.
Yeah. Yeah, it gets to the first question, Rich, and why is there that kind of concentration of that? And we've talked quite a bit about this, and the hypothesis is that there are a lot of iron oxides there in the ditch, and when the iron is under reducing conditions in the groundwater, it's mobile. And so while there's no oxygen the arsenic or the iron is able to move. It moves laterally while there's low pH zones, and then once it gets to the ditch, it's almost like there's this pH gradient as we move towards the ditch, and there's more oxygen. The oxygen, once that solution with the high levels of iron and arsenic hits the oxygen, then it changes form and it precipitates out, and we see an accumulation effect. And it's kind of like there's a reactive barrier there, like that. When it hits the oxidation zone, that barrier like causes that reaction to take place. So that's for that.
Any other questions? Okay, well, thanks all of you for being here. And now have the committee ask questions.
All on the phone.
Yeah.
Once you call them on the conference.
That's probably,
So it might be.
oh yeah. Just, you know,
Oh.
Yeah. Ramesh, we're going to call you.
Okay. Sure.
Okay, let's move here so you can see everybody.
There's the neck on the phone.
Yeah, I'm going to call him here.
I'm already just. I'm trying to because Amy's coming back on this one. So.
Yeah, yeah.
We're only presenting in the fourth chapter, not covering the first two, or the second two.
October the 2nd. That microphone.
Has been forwarded to an automatic voice message system.
Oh,
You have so much material, it's hard to get it all in there.
yeah, I took out chapter 3. I didn't include chapter 3 other than that one, like, but
Yeah, that was the one with the lower.
well, I just tried to call.
You can see me hanging out up here.
Let me stop this.
Yeah.